We've all watched large language models generate surprisingly coherent answers to complex questions. But what happens when we ask them to reason about uncertainty? Words like probably, might, and must aren't just conversational filler. They're the mathematical backbone of risk assessment, evidence weighing, and decision-making in fields like medicine, law, and quantitative finance. So the real question is, do these models actually understand probabilistic logic, or are they just pattern matching to statistical cues in their training data? A recent study built a benchmark specifically to answer that. Instead of vague prompts, researchers constructed over 14,000 questions designed to test strict logical entailment over probability. They used 15 distinct logical patterns. For example, if a premise states that an event is probably true, does the model correctly infer that it might be true, or that it is not definitely false? Conversely, does it correctly reject that it must be true? The models were tested under a strict yes or no constraint to eliminate hedging or verbose justification that could mask true reasoning. They evaluated 29 different architectures, ranging from small open-source models to the latest frontier systems. The results exposed a fundamental flaw. Most models weren't performing logical inference at all. Instead, they exhibited a strong, fixed response bias toward either yes or no, completely decoupled from the logical structure of the prompt. To quantify this, the researchers introduced a metric called the competence flaw. Here's how it works. You take a model's accuracy on all questions where the correct answer is yes, and its accuracy on all questions where the correct answer is no. The competence floor is the lower of those two numbers. If a model just blindly outputs yes every time, its floor drops to 0. If it's genuinely tracking the underlying logic, it should comfortably clear a 50% baseline. Out of 29 models, only 9 cleared that floor. And even the top performers were only marginally above random guessing. But the study didn't stop at raw accuracy. The researchers systematically varied the surface phrasing of identical logical problems. They swapped cultural names, changed contextual activities, and most critically, manipulated negation. The models completely fractured under these variations. When the exact same logical relationship was tested with different negation structures, accuracy dropped by up to 64 percentage points. Take the prompt phrase, does it not follow? That subtle syntactic shift confused almost every model, dragging performance down to near-chance levels. Meanwhile, phrasing like, is it incorrect, or is it invalid, performed significantly better. This isn't a minor quirk. It proves the models aren't extracting compositional rules. They're reacting to token co-occurrence, surface syntax, and the conversational cadence of the prompt. You might expect that simply scaling up parameters would resolve this. But the data shows the opposite. Increasing model size didn't reliably improve logical consistency. In several cases, larger models actually exhibited stronger response bias. Why does this happen? It comes down to how transformers actually process information. These models are trained via next token prediction on massive text corpora. They learn distributional semantics, how words statistically co-occur, but they don't maintain an explicit internal representation of probability distributions or formal logical operators. When a prompt introduces a probabilistic word, the model doesn't compute entailment. It predicts which response token is most likely given the surrounding context and its own internal activation patterns. Negation and logical operators are notoriously difficult for autoregressive transformers because they require compositional generalization. The model sees not and follow together and falls back on surface-level associations rather than applying a consistent logical rule. Scaling up parameters just gives the model a larger capacity to memorize these surface patterns, which is why larger models sometimes exhibit even stronger response bias. This fragility has serious real-world consequences. If an AI is parsing a clinical note that says a treatment probably works, or reviewing a legal brief stating a defendant might have known about a risk, it needs to actually weigh those probabilistic constraints. It can't just spit out a confident yes or no based on how a sentence is phrased. The competence floor metric gives us a much sharper diagnostic tool. It separates what a model actually knows from what it's just guessing based on response bias. The takeaway is clear. What often looks like reasoning in large language models is frequently just surface-level pattern matching, masked by a strong yes or no bias. Until we can untangle that bias from genuine logical inference, we need to be extremely cautious about deploying these systems in high-stakes domains. Scaling parameters alone won't solve it. We'll need explicit training objectives, structured reasoning frameworks, and evaluation standards that prioritize logical consistency over fluency. Because when it comes to uncertainty, pattern matching isn't the same as understanding. And if we want AI to handle real-world complexity, that distinction is everything.